Thanks everyone for coming. I'm happy to be here. This is my first time at AI2. So to begin, here's where we are today. We have tons of data, more data than we know what to do with, videos, images, whatever you want. We don't even know how to store this. Fortunately, we have deep learning. You have tons of parameters, huge number of layers to really soak up this data. And this has led to a lot of advances in NLP, vision, speech. So what possibly more could you want? Everyone should be really happy. Well, all of you know probably this story of the man who's looking for his keys under the streetlight. And the police officer asks, why are you looking there? And he replies, well, that's where the light is. And there's actually kind of a strange parallel between how researchers look at these data-rich problems because, well, that's where the data is. But that's not what this talk is about. This talk is about what's over here in the shadows. Okay? And to give you an example of what's there, so 2 years ago, I was talking to Shannon Peters, who is a paleobiologist at University of Wisconsin, who, with Chris Ray at Stanford, developed a database of facts about paleobiology. And we were thinking, wouldn't it be great to build a natural language interface into this database so you have researchers, students can come and ask really interesting questions to discover how the life formed on Earth. Right? And then I asked him, well, what kind of questions would you like the system to support? Maybe we can do something. And he was like, I don't know. I mean, we don't have any users, so I don't know what they want. Okay, so that's a problem. More recently, I've been talking to Monica Lam at Stanford, and she's developed this language called ThinTalk that allows apps to basically interact with the Internet of Things in a secure way. And similarly, we were talking about, well, wouldn't it be nice to have a natural language interface into this? So you could talk to your heater and turn and make sure it's warm when you get home and things like that. And again, the same problem, no users, so we don't even have data to get started with. So there's a bootstrapping problem. So you have users which depend on the system, but initially we don't have a system, which means that there's no users either, and we're basically starting from nothing. Okay. So this is not just unsupervised learning. In unsupervised learning, you have no outputs, but you still have your inputs, which means that you can go and annotate your inputs if you have enough money. But we're in a situation where we don't have the inputs, so what do we annotate? I don't know. This is also not really like zero-shot learning, where the assumption is that you train a model in other domains and you can reasonably expect to generalize in your target domain out of the box. Maybe it doesn't work as well. You have to have a few examples. But this is not quite the case in the application I'm going to be talking about. If you were building a natural language interface into a publication database for whatever reason, I don't know why you would want to ever do something like that. But suppose you did, then you might be able to understand the sentence kind of generically using kind of zero-shot learning. But I would argue that if you wanted to actually connect this with a database, venues doesn't just go to this database field venues. It probably is refers to one of these other fields, which it's not clear a priori which one it refers to, or it could even refer to something a little bit more complicated in a database. So there's this kind of domain-specific information that you actually have to learn. So zero-shot learning is going to be pretty hard. Okay, so here is the scenario. So your boss comes to you and says, great, we signed a contract. Tomorrow we're going to deploy our human-level natural language understanding system. Okay, and then so what do you do besides like quit? So this talk is going to be about 3 possible things you can do to save your pants. Okay, so covering the input space, on-the-job learning, and learning from users in increasing order of kind of user involvement, let's just say. Okay, so I'm going to start with the first one. This is a work that was published at ACL last year called Building a Semantic Parser Overnight. It was with Yushi Wan, who was an undergrad, and Jonathan Berendt, who was a postdoc at the time. He's now at Google, on way to being a faculty at Tel Aviv University. So to set the stage a little bit, for a while I've been interested in semantic parsing. So semantic parsing, for those of you who aren't familiar with, is the task of taking natural language utterances, mapping them to some sort of logical form such that these can be executed on a world or database to get out whatever you want, the answer or the result of a command. And for this talk, I'm going to think about the logical forms as being in Lambda DCS, this language that we developed, but you can also use Lambda calculus if you want. The details aren't so important, but intuitively what this is saying is that this is a set of articles, this is a set of things that appeared at ACL, and you're intersecting them and you're counting them up. And that is the semantics of this question. So there's been a lot of work on semantic parsing, statistical work dating back from the mid-90s with Ray Mooney's group. Luke Zettlemore has actually worked a lot on this. And over the years, people have been applying them not just to question answering, but instruction following and other things like that. And what I really like about semantic parsing is it really kind of allows you to support kind of an end-to-end task. You have user has some utterance, and the output is something that the user cares about, the answer. And this can be useful in a number of natural language interfaces. So to begin, so suppose you're building this publication database. What do? Well, the first thing you might do is we need some data. So there's no users, so you're just going to think, OK, what would a user, if I were a user, what do I want to ask? So you might just go and write down some utterances, and then you can go annotate them with logical forms, or if you're a little bit fancier, you can annotate them with answers, and we can infer in logical forms. But either way, this process is a little bit ad hoc and results in incomplete coverage, because you're just writing down questions that pop up in your mind. It's not systematic at all. And as an example, we released this web questions data set a few years ago. And after the fact, we realized that there were no questions that had numerical relations in them. So there was a big omission. We didn't realize at the time because we were just getting lots of questions and we were not being systematic about it. So instead of doing that, what I'm going to suggest is starting with what you have. So what do we have? We have this publication database. Or if you build a natural language into a fridge, you have a fridge, or you have a car. You have all these wonderful things. So why not start there? So each of these things defines a set of primitives. So think about the as fields in the database, if you like. And what we're going to do is stitch these primitives together in a very systematic way to generate all the possible logical expressions, all the possible things that you might want the system to be able to do, and then go backwards and figure out how you would actually say each of these things. Okay? So that's basically the strategy we're going to take if we have no data to start out with. So there's before that, I just want to kind of pop back up and think, OK, what is going on here? Normally in machine learning, you have data that comes from a distribution, and then you are trying to predict according to that distribution. But in this case, there is no distribution. There's no data. So instead, what we're going to do is trying to start with the output space and cover it, and then in the process, kind of cover the input space in a way that it can kind of, in some sense, work for all distributions. Yeah.
Your example on the previous slide was all metadata. So doesn't that constrain it? Like you can't ask questions about the actual content of the document.
Right. So the way this is set up is that you have a set of primitives, and we ask questions regarding those primitives. So if you had some things about like the topics of the article, then we would be able to support things like that. But it's basically whatever your database has. If it's completely unstructured, then this is probably not a good fit for that.
Previous example about forgetting to allow questions about numbers.
Yeah.
You still have that problem because you forget to include numbers in your primitives.
Well, these primitives are whatever. I mean, it's a full set that your database has. So you just make sure that you hit each of those items in your database.
So the assumption is
Yeah, so you have a database or a car or something, and then we're going to figure out all the ways you can say things that are supported by your database.
Is it a database or just a formal programming?
You can think about it as a programming language if you want. Yeah. Mm-hmm.
So you said you don't have an input distribution. Are you implicitly defining the uniform distribution by exhaustively covering things?
In a way, you can think about it like that. I mean, you can't. I mean, this is going to be an infinite distribution, so it won't be kind of completely uniform. But I wouldn't think about it necessarily as a uniform distribution because we're not going to be sampling from this. We're actually going to be try to tile up the.
It seems like the answer to that question, sorry we're derailing it, but we're kind of getting our head around the model. It seems like there is an interesting distinction here. When you think about the evaluation, you can evaluate, you measure the performance relative to some kind of uniform, or you can measure it kind of like they did in the PAC model, truly distribution free, which would be worst case overall possible distributions. So do you care about that stuff, or is it going to turn out to be irrelevant?
So later in the experiments, we're going to report accuracies which are averaging over the distribution that basically the uniform distribution. But the idea is that if you are actually deploying this thing, it's not that you are trying, you're actually trying to make sure you don't miss any of the things in the database. But yeah, if you like to think about it as uniform distribution, that's fine too. Okay, so there's two challenges I want to talk about. One is that the number of outputs is infinite, so you can't just enumerate all of them. And the second is that if you want to take a logical form and you want to say, hey, how do you render this in natural language, you can't just show a mechanical Turk worker one of these things. So the number of outputs is infinite, but there's some structure here, right? So if you have papers published after 2011, papers published in ACL, and you know how to say these things, intuitively you shouldn't need to ask for another example that is basically the conjunction after 2011 in ACL, because things are compositional. But life isn't so simple, because if you have these two examples, after 2011, before 2016, if you put them together, then it's not just after 2011 and before 2016. You have this new construction in between. And this is what I'm calling bounded non-compositionality, where if you have some primitives and you combine them together, language actually has higher level concepts or words that describe things. Like another example is like grandmother, which corresponds to the female parent of a parent. And the database might have female and parent, but it doesn't have the notion of a grandmother. So yeah.
How is this non-compositional? It seems like grandmother is a quintessential example of compositional. I'm missing something.
So grandmother is a word, and it maps onto basically a composite logical form. It's not a particular predicate. There's no one predicate called grandmother. Maybe another example is like afternoon. Afternoon, let's say it means after, starting time is after 12 p.m. and ending time is before 6 p.m. or something like that. And so the single word afternoon actually has, a lot of semantics, which isn't, if you just look at the token afternoon, it doesn't really reveal that. Okay, so the second challenge is I want to show someone the logical form to see how you would actually describe it. So we can't show them this, so maybe we can show people in natural language, but we don't want to just have to solve the natural language generation problem, which is hard. So the realization is that there's actually, this is one of the things that makes language difficult, but we can use it to our advantage here, is that there's many ways to express the same semantics in natural language. And so why don't we just pick one that is most convenient to us? So what we're going to do is pick some utterance as long as it captures the semantics of the logical form and is somewhat understandable to humans. So we're going to do something like this. Article with field CS at the most article site. So it's not completely grammatical, but if any human looked at this, they would kind of understand what's going on. Okay, so what we're going to do is we're going to define a small grammar The base rules are the fields in the database, and these domain general rules allow the possible combinations like intersection and argmax. And then as a result, when you generate from the grammar up to some bounded size, 3, you're going to get a set of pairs of logical forms with these canonical utterances which are capture the semantics but in a somewhat broken way. Okay, so we're going to now take these and go ask people, can you please rewrite this in a way that a normal human being would? And they would do something like this. Okay, so now we have examples of utterances with their logical forms. Now we have our data set we can train. I'll point out one thing just to build on this afternoon example. One thing that we weren't explicitly chasing, but we were pleasantly surprised to find is that there's actually a lot of kind of these what I call high-level concepts, right? You know, the word co-authored isn't just like a predicate co-authored. It's actually corresponds to the relation, the author equals the another relation author, and they're the same. I'm explaining that badly. I could write the logical form. And cats and dogs turns into pet friendly, and we already saw this example. So this is kind of a nice side effect of this approach. Yeah.
The co-author thing, if a paper only has one author, you might infer that author is a co-author. So you would have learned about who.
So there has to be, the co-author relationship would have to be, I am an author and I'm also not equal to. There has to be a not equal to in there. Yeah, so this one, I guess maybe we didn't handle that explicitly, but you're right. I mean, there's some subtleties there. Okay, so the idea, to demonstrate this idea, we tried this out on 8 different domains. Because remember, the idea is that it's really easy to just go into a new domain and build a semantic parser. So we wanted to show that we can do this. So here are the different domains: calendar, publications, housing, restaurants, basketball, recipes. And each of these took 5 hours. We got 12,000 examples total. We trained a standard log linear model that's using semantic parsing. And we compared 2 types of models, those that weren't using kind of lexical features on the domain, and those that, and this one that does. And the main point of this is showing that there's a considerable gap between if you use kind of stronger lexical features that's able to kind of capture the kind of domain-specific jargon than if you weren't doing it. Yeah. So this is accuracy on, so we took the data and we divided into train and test, and then we're just measuring the test accuracy here. So accuracy meaning, did you get the logical form completely correct on a given example?
So how exactly are you getting the lexical features?
So the lexical features we just define as indicator of, word shows up in your sentence, and I fire this predicate in the logical form. Right. So these are really kind of, simple features, but they're allow you to basically learn the fact that pet-friendly means allows cats and, dogs, or co-author means this thing, right? Whereas these things I think are wouldn't normally just fall out of having a kind of a generic model of language.
It seems like your generative procedure for generating data is going to produce a lot of either uninteresting or nonsensical expressions, like in articles published after 2000 and before 1950, something like that, which are no answers. How do you filter out all the junk?
Yeah, so that's a good question. So some of them are definitely not interesting. We bound the depth to, basically 3. So, and also for entities, we consider, a handful. Like for numbers, we just have 2 and 4, and for people, we have like Alice and Bob or whatever. So that kind of constrains a number of things. It's a little bit tricky because a priori we don't know which combinations of predicates might lead to kind of this bound non-compositional behavior. So as an extreme example, if you say, meetings, I guess, I don't know if people have meetings on Saturday and Sunday, but if they did, then meetings on Saturday and Sunday would be, someone might type weekend instead. And so we wouldn't actually know this, so we might actually have to generate all pairs of days. So, I mean, it's a good point that we will probably want a little bit more kind of adaptive way of generating logical forms that we think are interesting. Okay, so let me summarize this section since I have bounded time and I have 2 other things to get through. So the main issue is that we don't have an input distribution to start out with, so we basically kind of try to cover the space using this grammar plus paraphrasing. These high-level concepts that emerge from people annotating this data, I think, is really interesting and worth exploring a bit more. One kind of lesson of this is that if you think about natural language semantic parsing as connecting language with logical forms, it actually is not the case that the bridge between natural language and logical forms is necessarily the hard part. Because here we show that you can actually easily go from logical forms to one particular point in the natural language space, even though it's not great. The hard part is kind of covering all the different ways that you can express something in natural language. And this is what the humans are focused on doing in this task. We tell them to paraphrase, so they spend all their energy on actually figuring out how to use their language abilities rather than answering questions and figure out or solving puzzles. It'd be interesting to try this to non-language applications as well. So I did talk about that offline. Okay, so now you go back to the boss and you say, look, we deployed 8 different systems overnight. Should be really happy. And the boss says, well, you got only 58.8%. I want 90% accuracy. So you have a really tough boss here. So now your job is still on the line. So you have to go back to a drawing board. And what are we going to do? So the next part is going to be on-the-job learning. This is a NIPS paper that showed up last year with Keenan, who's an undergrad with us, Arun, who is one of my PhD students, and Chris Manny, who many of you probably know who he is. So the situation is we have 0 data and we want 90% accuracy. So this seems utterly hopeless. But we're going to cheat a little bit, and we're going to use humans. Okay? And there's kind of a precedent of this kind of these shenanigans, right? So we have Mechanical Turk, where a human is in a box that pretends to play chess, or you have the Wizard of Oz. These nice examples serve as motivation for us. But we're not just going to settle for having a human in the box and doing the task, because then what's the joy in that? We want to actually leverage that setting to actually do some learning. So this is what we call on-the-job learning. So here's a young chap who is on the job making your horseshoe or whatever, and so delivering some value to some customer. And when the young chap doesn't kind of know what to do, he's going to ask the master. The master is going to tell him. And over time, the young chap is going to just get a lot better at doing what he's doing, and then rely on the master less. Okay? So learning on the job is what we're after. So the motivating example here, we're going to move away from semantic parsing and talk about sequence labeling. So imagine you have a disaster and people are tweeting left and right about all sorts of things, and the goal is to tag these tweets with where resources are at various locations. So just think about it as a sequence tagging task. The model is going to be a standard conditional random field. And now I'm going to show you kind of an example of what the model is going to do to ask for help. Okay? So I get a tweet, soup on George Street, hashtag Katrina, and the model initially is really bad. It can't just predict and return to a user because that will probably be wrong. But what it can do is it can ask for help. So suppose it fires off 2 queries at these locations, saying, hey, human, please tell me what the label of these are. And of course, humans are slow, so you wait maybe 3 time steps, and then at this time step 3, this one returned as a resource, and this is incorporated as evidence into the graphical model there. And this one is still outstanding, so you wait a little bit more. This one comes back as person, which actually happens to be wrong, and maybe you realize something's up, so you send off another query to double check and wait a little bit, and then it comes back as location. Now these are added as potentials, and then maybe you have enough confidence about the tag, and then you return the result. Okay? So that's kind of one run through of a possible scenario. So the main question is, which positions should you be querying, and when should you be querying them? So this is kind of real time, on the fly, you're making these asynchronous requests. So there's trade-offs here. If you want high accuracy, you presumably want to go and query a lot, but that's going to be pretty expensive. If you want to return to the user in a short amount of time, you can actually query more heavily. For example, if you fire off 10 requests, then the first one that comes back, you might just take, and that will have lower latency, but again, that costs money. So how do you balance all these forces in play here? So our approach is basically write down, put on our Bayesian hats and just write down kind of what we want, and then we'll figure out how to optimize this. So there's going to be 2 computational challenges. There's combinatorial many ways of querying, and also there's, we're making all these asynchronous requests, so we have to manage the time or model the time properly. So for a while, we tried to write down some equations using decision theory, and we just got really confused because the time asynchrony and the kind of the amorphous structure just got us confused. And then we wrote down a game tree, and it became really clear. So that's what I'm going to do. So in the beginning, the agent has several choices. You can query a label, query another label, or wait. So let's suppose we query the label for the first position, and then query the label for the second position, and then we wait. Wait is an action that hands control over to nature, and nature is going to, nature meaning the human in this case, is going to respond with something. So at this point, there's 2 outstanding queries. So either Y1 could come back or Y2 could come back. And each of these could be some label. And also there could be some random amount of time that has elapsed. Okay? So these are the dynamics. And then after maybe this one comes back, then it's the agent's turn, and this kind of goes until the agent decides to turn in the result. Okay? So I'm going to dive into this little piece here and show how the transitions work.
Next, you ask another agent I see that you have Y1 and Y2 in the other levels. So you ask another person for the confidence result?
So the actions you can take are query, which actually just sends it out to a pool of workers, and someone picks it up. It might not be the same person.
So under this model, if you decide to wait, you can't stop waiting until somebody gets back to you?
Yeah, so the way we've set it up, you just wait until someone gets back to you. You can also put in a timeout if you want. We didn't actually do that. Okay, so the environment model is this basically distribution over these states conditioned on what happens when you say wait. Okay, so the first thing that happens is that there is some random time that we model as a gamma distribution. And then what is the label that comes back? The label that comes back is based on your CRF model. You have a base model that has some posterior belief over what the possible labels are. And then in addition, there's we assume that there's some Turker noise. So 70% of the time you get the right labels, 30% you get some crazy thing. Okay, so that's basically the model there. And at the end, at the bottom of the game tree is the utility function that says how good is this state. So remember, a state is you're at a particular point in time, you made a bunch of queries, and then you turned in some result. Okay, and the utility is basically the accuracy according to your turned-in result. You can think intuitively this should be basically the entropy if you were using the log loss. And then you get penalized for waiting some time, and you also get penalized for spending a number of queries. Okay, so given this game tree, now we have mathematically specified what we want to do. We just want to find the action that maximizes the expected utility, and there's a recurrence that you can write down. But this is intractable to compute exactly, so we're going to use Monte Carlo tree search to do this. I'm not going to go through the details, but roughly, basically, I'm trying to build estimates of the values of each of these nodes by basically sampling kind of the most promising parts of a tree. So I'm going to, at each node, look at children based on how good they are plus something for exploration. So again, sorry, I'm not going to go through details, but yeah.
Can I ask one question on
Yeah.
that? Often in MCTS, you try to sample down the tree by doing very quick but very deep dives. But if your deep dive involves a weight, how does that?
If you're deep diving in,
Involves a weight action. Then
yeah.
you actually simulate it.
Yeah, so that's the point of this next slide. And the idea is that if you were just sampling from this node, then every time you reach this node, you're going to sample a different child because you're weighting a gamma distribution. With probability 0, you're actually going to hit the same thing, right? So there's this technique called progressive widening due to Coulomb, and the idea is that we're just going to restrict the number of children to not let it grow too fast. Okay, so in particular, we're going to ensure basically if you visit this node n times that there's on order square root of n children, and on average each children has square root of n kind of samples down it. And then so as you sample more, you're kind of growing the number of children. And this turns out to give you consistent estimates. Okay, so to recap, the algorithm is the system gets an input sentence from the user, and it's going to basically make a bunch of queries. Each query, you run MCTS to figure out what to query or to wait if you need to, or to turn in the action. And then at the end, you're going to return your prediction based on the evidence that you've masked to the user, and then you update the parameters based on your model. Okay, so this part isn't fully Bayesian because we're not reasoning about how the parameters get updated when we're making these actions, but the Bayesian part is really kind of in the querying, in the inference. Okay. So we ran some experiments on name entity recognition on the standard Connell data set. And we looked at what happens if you just query every position k times. Or there's a threshold which basically looks at your model probability and queries to drive the entropy based on how much uncertainty you have each position. And then this is the system I discussed. So this is F1 on the test set. And this is our method. And you see that the threshold and the lens outperforms, basically these methods that are kind of querying non-adaptively. Even if you query 5 times per token, you're not doing that well. And if you look at the latency, the amount of time you actually spend, lens is actually much better than if you have to query a lot. And similarly, with the amount of money you spend, we're also much better than having to make a static number of queries per one per position. Okay, so here's another comparison. This is not really a fair comparison. So we're comparing online learning, which trains the model on the data it's seen so far, and then just predicts according to that model. And so this is online learning. Initially, model is bad, and then it gets better. And the thing I want to point out is in on-the-job training, we're actually able to ask for help before we make a prediction. And this is a key step that allows us to maintain high accuracy because as long as we're not confident, if we see unknown words, no problem, we just query, and then we can keep our high accuracy and then still learn on the job. Yeah.
It looks like the red line is getting worse with time.
Yeah, so I think that's probably just kind of noise because over here there's just not many samples that you're dealing with. So I mean, I think this is, you should think about this as kind of a flat line around like 88 or so.
So in your model, you're modeling human as the gamma distribution over time, that's how likely they're going to answer.
Mm-hmm.
Does that match with in your experience with the triggers?
Yeah, so that's a good question. I don't have an immediate answer to that. I think, I mean, let's see. I remember it was not, I think it was a reasonable thing. Of course, it's not exactly a gamma distribution. What I'd be more worried about if there's actually kind of dependence on the examples, because here we're modeling as a gamma that doesn't depend on anything. But of course, you know, maybe a harder example, people might be waiting longer or something.
Parameters are not learned, for example, it's over.
Yeah, so there's just one gamma distribution. And furthermore, there's, you might worry about kind of heterogeneity among workers, which we're not modeling either. Yeah.
So I'm really confusing about it. Across the time, how you, at the end, how can you just get rid of the human resources and just rely on the model? And
so I'm not sure you would be able to completely wean off humans. I think you would have to wait a very long time. But the point, I guess it's not shown in this slide, is that you know, the amount of time you have to query humans goes down while this accuracy is still remaining flat. Yeah, so there's a plot in the paper I can show you afterwards that shows the amount of time you spend querying. Yeah. Okay, so this work is kind of connected to many things, online active learning, active classification. In online active learning, you're improving the accuracy over time, but you're querying the crowd after the prediction, which means that you can't maintain high accuracy. Active classification, you're querying before prediction, but usually they're not necessarily trying to improve the model performance over time. And this actually connects with a lot of work that recently on trying to aggregate information from the crowd. And you know, we could probably use some of those ideas to improve our model of what basically crowd error. Okay, so we set up this on a job learning setting. To give some clarity, we set up as question?
Yeah, quick question. So with this gamma thing that you're modeling human, I think it's really critical to really understand what each person will do, because that will guide your tree search, right? So whether should I query because this person is really slow, or this particular example, there are not that many people picking up this hit. That seems pretty critical to precisely model either per question or maybe not per worker, but at least per question, that latency model.
Yeah, I mean, it's a fair point. I think it's also something that's pretty difficult to model precisely. And if you're going to model, I think you have to kind of your model has to be correct. You don't want to be kind of overconfident and say, yeah, this is going to take like 200 milliseconds when it actually takes 5 seconds or something. So I think our estimates are basically fairly conservative because we basically say, you know, it's one gamma, but we're going to have the gamma have a wide distribution, so we can, you know, allow for the case that if people just take a long time. But you're right. I mean, I think this requires a little bit more attention. Okay, so the Bayesian decision theory gives us some guidance, and you know, to make things work, we use MCTS. I think one kind of thing I'm wondering about here is that in general, doing the full Bayesian rollout is expensive, but it turns out that I don't think there's some structure in this problem that makes it not as bad. It's not just a kind of a full game tree where you know, you're actually working with the adversary. This is some structure that we'd like to exploit a little bit more. And also one interesting thing, besides modeling the crowd better, is that how can you actually have the crowd give you more? So right now we've constrained ourselves to basically asking people to query individual positions, but you might ask people to query label a window or give you some other sort of partial annotation or verify other people's work. So I think there's a lot of possibilities, and if you you can consider all these possibilities as just operators and learn kind of when to apply these things. So that's kind of a lot of work going forward. Okay, so now you go to a boss and you say, okay, we got our 90% accuracy. Well, it was actually 88.5, but you round up, you know how these things go. And the boss says, well, you know, what? You're paying people to do this? They should be paying us to label our data. So this is going to be pretty hard. So what are we going to do now? So this last project I'm going to talk about is we're kind of work in progress. It's with Sida, who is co-advised between Chris and me. And the situation is this. We have zero data, zero money, and you still want something good. Okay, so this is getting pretty, you're about to quit at this point. So let's take a step back. What are we trying to do here, right? So you could be trying to parse sentences. But in some sense, that's kind of not what we're trying to do with these semantic parsers. We're trying to allow users to actually do something in the world, like schedule meetings or get questions answered or so on. And language is just a kind of means to an end. So with that view, okay, so this is, I guess, the practical way to think about it. So the more philosophical way is thinking about what Wittgenstein said, which is that language derives its meaning from use. So Wittgenstein's developed this notion of a language game, which we're kind of trying to operationalize here. So language games actually mean kind of multiple different things, but one particular thing that he famously created was this idea: you have a builder and an assistant, and the builder says to assistant, slab, beam, and and the assistant would pass the builder the necessary tools and basically materials for the builder to do something. And this is an example of kind of a primitive language where you just kind of create some language on the fly for your activity at hand. Okay, so that's the inspiration for this work. And so what we did is develop a game called Shared Learn, actually. Sorry. And the way it works is that I'm a user, and I want to convert this block configuration into this one. And the only thing I can do is type into this box. Okay? And in the beginning, the computer has no idea what I'm typing. So I can type anything here. Like I can type remove cyan. It doesn't know what I'm doing, so it does something random. But then I can give it feedback. So I can say, that's wrong. That's definitely wrong. Wrong, wrong. And this is right, so I'm going to click this. And that gave a training example. So now I can remove orange and do the same thing. Now I can remove orange, and it understood what I meant, and so on. And you can see that we have this curriculum of different tasks for the users that get more and more complicated. And the idea is that throughout time, the assistant or the computer is trying to help the user accomplish its goal. And in the process, the user has taught the computer some language. So it's kind of a symbiotic relationship there. OK, so this is the setting. Only the human sees the goal. The computer can only perform actions. And initially, the computer knows nothing about language. So the human says something. The computer is going to parse it into a set of logical forms. And it's going to rank those logical forms, execute them, and show the resulting states to the user. And the user is going to go down the list and say no, 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 yes, and return that state. And given this supervision, the computer is going to update the parameters. That state's going to actually become the next state, and the game proceeds. Okay? So the types of logical forms that we're dealing with are ones which are generated by a small grammar. So you can add and remove. You can form kind of sets of blocks by taking diffs and using negation and looking at our superlatives on the leftmost or the rightmost and so on. So it's not it's not crazy complicated, but there's some compositionality there. So standard log linear model, online learning updates. And we tried this on Mechanical Turks. We had 100 people play this game. Whole thing took about only 6 hours, and we got 10,000 utterances as a result. So one of the most fascinating things about this project is just kind of we basically told people you can use any language you want, you can type whatever you want. Your goal is just to win the game or do well in the game. So it was interesting to see what people do. So these are the players that did the best. So meaning that they had to kind of scroll the least amount of time. And you can see that this person developed some sort of like shorthand, remove cyan position 1. This person used natural language more or less, and this person used something very similar. Some of time people are able to do well even if their natural language actually falls outside the scope of our semantics. So for example, numbers we don't actually handle, but the system is robust enough that the person can kind of scroll a little bit and correct and get the right action. So these are the average players ranked 20 to 50, and you can see that these utterances are maybe a little less kind of concise. And if you go down to the worst players, this person actually didn't put any spaces in the words, which means that our features were not able to generalize. So therefore, this guy did really badly. And this person just typed random stuff like laugh with me, which obviously isn't going to get you anywhere. There's some interesting things. One guy used Polish. Another guy used Polish notation. So it was actually kind of fun seeing what people did. And one of the things that I think is a high-level takeaway is that normally you think about language as, okay, there's these things called English and French and German, and we're just trying to understand how these things work. But here, language is kind of a communicative system. It is really a two-way street between what the capabilities of a computer are and what the human can do. So I think it's a pretty interesting test bed.
And how did you motivate yourself for the motivation? How did you motivate the people to play the game?
Money, we pay them.
So that's zero money.
Yeah.
You said you're
Well.
parsing these to a logical form.
Mm-hmm.
How are you doing the parsing? Are you inducing the grammar and the lexicon from?
So I'll say a little bit more about this. So we have a string that we see. We break it up, it's a bunch of words. And we have a grammar that generates the candidate logical forms. So there's going to be, let's say, 200 logical forms. And we use a beam search to kind of guide the search. And then given a logical form and a sentence, we basically fire all pairs of word predicate features. So it's not a parser in the sense that it's building things compositionally up, but it is a parser in that it places a distribution of a logical form given utterances. So that allows us to basically not have a lexicon to begin with, and we can learn kind of any kind of word order that you give it.
So you use features of the user's sentence to rank the different logical forms you produce.
Yeah, exactly.
Okay.
This is interesting, but if you take this test to a little more, even slightly more complicated example, like you have 2 lines of blocks, then the number of possible logical forms that you produce will just blow up very quickly.
So then we actually, just having more blocks doesn't necessarily blow this up. But if we wanted to add more predicates here, you're right that it would blow up. And the way so next we're going to try to do this. And there's some ideas. One idea is that the curriculum, right? So in the beginning, you start small and you search over logical forms of a certain size. And in the beginning, the system doesn't even know colors, right? But you can use remove red, add cyan to basically teach the system colors. And now with colors, and basically if you know colors, now you can understand larger utterances where colors are just kind of you know what they're talking about. So I think if you design a curriculum properly, you can actually bootstrap to much more complicated logical forms.
Yeah, I'm thinking like questions, like natural questions, like, oh, find me the best Italian restaurant in Seattle area. Then kind of trying to have humans teach that grammar to a computer, that would be a lot bigger problem.
Oh, so if you wanted to actually have, like the virtual agent setting, which we're also thinking about, then you wouldn't want to start from scratch. So this was kind of more being purist and saying, what happens if we start from scratch? But in reality, you probably actually want to share the model between all users. So here, every user got its own model. We would probably want to not start from scratch, share parameters between users, and you could probably reach a higher point that way. But still the idea that you should be able to kind of give the system feedback, and it should basically, in a real-time manner, improve itself is something that's, I think, the central thing I'm trying to convey here. Yeah.
So to set up the system, you have to define the space of all actions the computer can take. Does that let you at least bootstrap the language somehow? It's like, there are so many different things that might need to be described because that corresponds to the label?
Yeah, so this definitely relies on the fact that we can enumerate our action space. Otherwise, we kind of have nothing to kind of work with because we don't know what the language is. All we know is what actions you can take. Yeah. Okay, so let me go on. So one thing that when we were playing around with the system that was a little bit not satisfying is it wasn't seeming to kind of learn fast enough. And when we're doing normally online learning, right, you have these large data sets, you can take multiple passes, things kind of work out in the end. But here you're in an online learning setting where everything kind of matters. And because you have like 5 examples, you really need to pay attention to each one. And so if you told the system remove red, and it means remove with red, then and then you typed in remove cyan, what do you think remove cyan should mean if you didn't know words? Well, it could be anything, possibly, but it probably doesn't mean remove red, right? Whereas the model currently does the opposite. It says, oh, it's definitely remove red because that's that's the only thing I've seen before, so yes, it's probably remove red. So there's some missing intuition, this mutual exclusivity. So this is this shouldn't be a hard constraint, but it's kind of this natural aspect of language that we tend to reserve tokens to reference different concepts. I mean, we have synonyms sometimes, but by and large, the first order effect is that distinct words refer to distinct concepts. So how do we capture this? So we again turn to kind of decision theoretic thinking. So several years ago, worked on kind of these pragmatic models, and Noah Goodman and Mike Frank have further developed these things called RSA models that try to capture kind of pragmatic reasoning in language. So the idea is to think about the computer as a listener that says, okay, I'm given an utterance, and I want to figure out what logical form it is. Okay, so what's going on here? Well, let's see. Well, where the utterance came from? It came from a speaker who had some prior over logical forms and then generated according to the speaker's model of sentences given logical form. So this is kind of happening inside the listener's head. And what is a speaker? The speaker also has, says, I want to generate X given Z. Well, it has some prior over utterances, and I'm going to choose something that is based on kind of a base listener of logical forms given utterances. So you basically have these system of equations that allow the listener to reason about kind of the speaker and the speaker to reason about the listener. So in addition, we're just going to put a small beta here to sharpen the results. So think about beta as like 3. So this is the RSA model that Michael Frank and Noah Goodman came up with. So just to kind of give me a numeric example. So here, you saw remove cyan. If you just take the original model, it's going to say 60% remove red and 20% other stuff. But if you iterate this 2 times, so here's a speaker and here's the listener, then you see that the distribution over logical forms conditioned on the sentence is now shifted where the mass is actually rightfully not in remove red. Okay, so by doing this kind of pragmatic reasoning, you kind of get the effects of this mutual exclusivity. Okay, so this part I'm going to actually skip. So this is basically, there's this P of Z and P of X you have to estimate. So we have some kind of estimates that you can build online. I'm going to skip the math here. OK, so the setting is receive utterance from a human, predict the denotations by this listener, and get some feedback from the human about which one is correct. And you update the parameters of the semantic model, and as well as these P's and Q's for pragmatic reasoning. So how well does this work? So here is a plot that shows without pragmatics, with pragmatics, and where this line is kind of indifference. So initially, when we looked at this, we were kind of disappointed because it doesn't seem to really change very much. But then we thought, well, why should it change? So we then basically stratify into the red, which is the top players, the green, which is the mid players, and the blue, which is the bottom players. And notice that the bottom players definitely don't benefit. These are people who type random garbage into the system, and so why would they benefit from kind of pragmatic reasoning? And we notice that the top players actually do benefit, right? And this makes sense because when you're modeling the pragmatics, you're saying, I'm a listener. I think the speaker is being a rational agent that's trying to maximize the utility and the chances of successful communication. And if that's happening, which it is happening with the top players, then we're going to get a boost. But if that's the wrong model of what's going on in the other person's head, then you're not going to get a boost. So this was kind of actually reassuring. OK, so to summarize this part, this is kind of a new language learning setting, which I think is just the beginning, I think. There's a lot to explore here. And I really like this idea of having some downstream goal drive the language learning rather than a priori saying, I'm interested in language learning. Because then you have kind of this, not only the supervision signal, but you can expect language to kind of evolve kind of more organically. So here, I guess it's important to remember that language is kind of a two-way street between two people. So both the computer and the human are kind of adapting to each other, which introduces kind of interesting dynamics. We're doing everything online, which means that pragmatics is kind of helpful to ensure kind of faster learning. And the way to really think about this work is not that we kind of create a data set from Mechanical Turk, but really as an environment for doing kind of language learning studies. OK, so finally, you go back to the bus. Now all the users are addicted to our game. Well, at least they're accomplishing their goals, I guess. So maybe there's some success here. All right, so let me summarize in the last minutes. So we have this bootstrapping problem where no system, no users. And what do? We talked about 3 different ways. Here, humans aren't really in the loop. I'm just trying to basically set up a seed model by covering the input space carefully. Here, we're basically leaning on users to help as a kind of a crutch to help us make better predictions. And here, we're actually having the users themselves be the ones who are giving supervision. So 3 remarks. I think the success of kind of machine learning is really kind of contingent on having the right data. And a lot of times, data comes in this kind of neatly cut up, packaged ingredients where if you're the ML person, you just kind of stir them together and you cook yourself a meal. But of course, a lot of the work is actually in the preparation for those of you who cook, and you probably know that. And what I want to think about is the kind of the joint process and how you can make this more efficient and better. And I think the second point is not to think so much about data sets, but about kind of environments for this kind of interactive learning setting. And finally, I think one driving kind of practical motivations is that systems should get better with use. So instead of having this train and deploy kind of mentality that we are used to in machine learning, we should really be thinking about kind of learning as an online, truly online process where you have a system, it's out in the wild, it's making predictions, but it's also kind of improving on the fly. Okay, so all of our code, data, and experiments are on this site that we've been building called Codolab Worksheets. That's actually, just to say a little bit about it, it provides a kind of IPython-like notebook format for visualizing your experiments, and you can basically go and type in arbitrary Linux commands and monitor your jobs and so on. So it's kind of, you should check it out. Okay, so thanks.